Hello, welcome to the vlog for the compute vlog or whatever I'm calling this. Um, compute rants. I'm just going to be talking about stuff I've learned, and future Sam will thank me. So I'm just looking at how do you perform lots of calculations really fast on a CPU, and the thing we're going to be calculating is this Roche potential. Here you can see S1 is given by this, S2 is given by this, R is just the x and y distance, pretty much like the in-plane distance. Um, and the way we're going to compute this is with a few different methods. We're going to compute it on a grid, and the grid I've chosen is 256 by 4 each way, and it's a 3 by 3 grid. So if we do the maths, 256 times 4 equals 1024, hopefully, yeah. And then if we raise that to the power of 3, we get roughly, what is that? Roughly 1 billion data points. So we're going to be computing this for 1 billion data points and seeing how quickly we can do it. Now here I've got a Python example. Here is the actual calculation. This is not at all efficient. It's some AI slop, is exactly what it is. And you get that it takes this many milliseconds, which is roughly 4 minutes. Now, I'm going to show you how quickly it runs in C++. That's the first optimization. Just use a different language. So in C++, go clean, oops. I spelled that wrong, didn't I? Clean, make run. Okay, so now it's going to start computing. Mind you, now that we've got an OBS and recording and stuff, it's going to be a lot slower. But the first one we're doing is just a super naive method, exactly like was done in Python. And you can see it's going to take roughly, give it a second, it's thinking. And okay, this is really disappointing. It should have done this. We've done some. There we go. Okay. 4 seconds, but that felt a lot longer than 4 seconds. Okay. But now you'll see later on, we're going to get to this optimized run, which computed it in half a second. By the way, the 4 seconds was just for the actual computation itself, not for the array initialization. So that's why it seemed like longer than 4 seconds. Well, it was longer than 4 seconds. Anyway, so the actual computation is 4 seconds, and then this more highly optimized one, 500 milliseconds. This one here as well is changing not a lot, and this is still 1 second, so like a 4 times increase there, 8 times increase here. Anyway, yes, let's jump into what the hell I've done. So I should go into the code here. This is the C++ code. So this here is the highly not optimized one. This is the one that really sucks. All AI slot benchmarks, so maybe I should check more carefully about making sure it's doing what I told it to do, but I have faith. And then this is the much more efficient one. And then these are some other benchmarks I was just doing. Okay, so let's see what's happening here. So what we have is we have a grid of points and we're trying to compute a function with it. So we have an X array, a Y array, and a Z array. And these are each 1024 elements. So in the slow, highly not optimized one, actually, first of all, I don't have these stored in arrays like this. I have an array of arrays, and it's all like arrays of pointers. It's a big mess. And basically, that original structure is not contiguous memory, which means the memory is not right next to each other. So when you actually have to compute anything and you have to send stuff from your RAM to your CPU, it can't just load in like a whole block at once, just easily see where everything is. It has to search through your RAM to find everything. And that is obviously very, very slow. So that's part of the reason the first one is so slow. But actually, from my benchmarking, it doesn't seem like that's the main reason. The main reason is because of the lack of SIMD. So this is basically how the computation goes. Your arrays are in RAM. And this contains your X array, your Y array, and your Z array. Okay? And then your CPU wants to do some computation. So what it does is it loads it into your what's called L1 cache. L1 cache. Okay? Now, what this is going to do, going to load it into L1 cache, so this is basically loading it into your CPU's memory, right? This is a lot easier to access than your RAM. But here's the thing about your cache. I actually don't know how to say it. Right. Here's the thing about the cache. Okay, I'm going to stop now. It is actually really, really slow to fetch that memory from RAM to your CPU. It's actually a very slow process. So instead of just taking one measly little byte, instead of taking one byte, it's not what it does. Instead, it takes a whole block. I believe it's 64 bits at once, right? I'm just going to check that with my reference. Oh, wrong reference. Sorry, guys. Oh, God. Okay. Here we go. So, what it does is, 1 second. Sorry, that was silly of me. Not bytes. Not bytes, but not bits, but bytes. 64 bytes. So it takes 64 bytes at once. My each double data type is 8 bytes. So what it does is it actually loads 8 bytes at once. So what it'll do is it'll fetch memory and it'll give you an 8 byte chunk of X, Y, and Z. And it's actually easy if you've got 8 elements. So not 8 bytes, 64 bytes. Each double is 8 bytes, so 8 elements times 8 bytes equals 64 bytes. Okay, correct. So it's going to load some of the array, part of the array, it's going to load 8 elements at once, okay? And now these are in your cache, right? So these are in the fast memory. And then there are two ways you can do this. So the slow way, the way that took 4 seconds instead of half a second, is it just will load these into, I forgot the size of registers. I believe it's 64-bit registers. Okay, so then, so the way CPU works is you have your part that does the actual computation, and inside there are registers, right? And these hold things for not very long. These are meant to do all the calculations for things in the registers, right? And then above that you have the L1, L2, and L3 caches, right? And this is kind of like the RAM for the CPU. You can imagine it like this is a bit of a simplification, by the way, and I'm excited to learn more about it. But anyway, so this is like the RAM of your CPU, and then above that is the actual RAM. Okay, so once it's got it in these caches, then what it can do is it can load one element into a register at a time, X1, Y1, and Z1. and then it can perform all its operations with these. Actually, really, there should be an output as well. Out, out, output. But anyway, point is, it will do things on individual elements at a time. However, what you can do, and this is what gives you the 4 times speed up straight away, is instead of doing it for, oopsies, why did I erase that? Instead of doing it for individual elements, you can use the SIMD instruction set. SIMD, SIMD. Okay. And what this does is, instead of loading it into those small registers, it loads it into a 256-bit register, which means you can store 4 elements at once: x1, x2, x3, x4, and so on and so forth. And then it performs a vectorized operation. So say you want to add these two things or multiply these things. It will do it element-wise, so x1 plus y1, y1, and it'll do all this element-wise, but it'll perform it on all elements at once with a single CPU instruction, basically. And that is where you get the 4 times speed up with using the SIMD instruction set. And then the final piece of the puzzle, the reason was 500 milliseconds instead of 1 millisecond, so that gives you from 4 seconds down to 1 second. And there's one final thing to get to half a second, which that is just to use parallelization. So this all happened not on a single CPU, but on a single CPU core, right? And for example, my CPU has 20 cores, right? So what you can do is you can split these instructions on different cores, and then you can perform all of these at once. And the idea is, before you do any of this, you split your array into blocks, like let's say 20 blocks, right? And then each of your cores is in charge of a separate block. Now, there is one issue. You may notice 1 second to half a second. Why did we not get a 20 times speed up? And I believe, I should further investigate this, but I believe it's just a bandwidth issue, right? It's just trying to take so much memory. So, for example, this 1 billion, let's see, we have 1 billion data points roughly, so that's 10 to the 9 data points times 10 to the 8 bytes, right? That gives you, so yeah, it's 4 AM right now, so that's my excuse for all of my, no, it's not 4 AM, it's 2 AM, Jesus Christ. I shouldn't be doing this at this time, I should be in bed. Anyway, so I have 10 to the 9 data points, because 1024 by 1024, yeah, on each length, so 1024, 1024, 1024. So if multiply that, you get roughly 10 to the 9, so 10 to the 9 data points times 8 bytes per double, right? That's 8 times 10 to the 9 bytes, which is 8 gigabytes. Alright, but then how many array elements do I have? Well, really, I have 4, x, y, z, and then my output. So 8 times 4 equals 32 gigabytes. So computing this requires 32 gigabytes of RAM, right? So when I'm computing it in 1 second, I'm moving 32 gigabytes in 1 second. And I believe that is why when you jump from 1 second to half a second, you know, now you're doing 64 gigabytes per second, and that's pretty damn quick. So the bottleneck is how quickly we can actually fetch that memory, not how quickly the CPU can compute those things. So yeah, anyway, in summary of all of this, Python takes 4 minutes on a CPU without this parallelized SIMD, sorry, in C++ without parallelization and without SIMD instruction set, it takes 4 seconds. With the SIMD instruction set, which allows you to compute multiple things at once, like 4 things in your register at once, that brings it down to 1 second. And then furthermore, if you allow for parallelization, so running this on multiple cores, brings it down to half a second, where the main limitation appears to be bandwidth. So I'm getting roughly 64 gigabytes per second at 0.5 seconds, which is pretty insane. Anyway, thank you to whoever's listening, mainly Future Sam. And good luck, Future Sam. Hopefully don't encounter many bugs.